Hi, so in today's lecture, I'd like to talk to you about the differential form of Ampere's law, and I'd also like to discuss in some detail the difference between EMF, the electromotive force, and the potential difference. What's the difference? Sorry, couldn't resist the pun. Okay, so before we get too far into talking about what the real difference is between the electromotive force and the potential difference, maybe we should go all the way back to the beginning of our course and talk about the definition of potential difference. Now, in the class that I'm teaching right now, we're using Purcell and Morin's Electricity and Magnetism, 3rd edition here, okay? And so to quote them, they give the mathematical definition of the potential difference, which is that you take the electric potential at some two positions, we'll call them initial and final, and you subtract those two electric potential values, VF minus VI, and then that gives you the potential difference, delta V. And then that is going to be equal to the negative integral of E dot ds. Okay, so you're doing a line integral of the electric field. It's the negative line integral of the electric field over the path. Here, E is the electric field, and of course ds is the little displacement vector. Okay, so now if you look at it, the quote from the textbook, and I want us to think very hard about this quote, with the minus sign included here, the potential delta V is the work per unit charge done by an external agency in moving a positive charge from P initial to P final, your initial position to your final position, in the field E. The external agency must supply a force, F external, equal to minus QE to balance the electrical force, F equals QE, hence the minus sign, okay? All right, so basically, what is this saying? It is saying that the potential is defined so that the work per unit charge done on the charge, okay? So remember, sometimes from Physics 1, we talk about the work done on something versus the work done by something. When you're talking about your definition of your potential difference, it's the work done on the thing, not the work done by the thing, okay? Now, when you talk about your EMF, your electromotive force, that is the work done by the thing. So they're going to be related by a minus sign, all right? Okay, so in order to understand this, let's look a little bit, remind ourselves of motional EMF. Now, we covered this in a previous lecture, but to remind you, you have your magnetic field into the screen here. It's a constant magnetic field for a lot of motional EMF problems, okay? The into the screen bit is indicated by the green X's pointing into the screen here for the magnetic field. Now, you have a conducting bar of length L, and that conducting bar is moving, in this case, to the right with a velocity V, okay, through the field. Inside your conductor, you have these free electrons, free charge carriers, basically. Due to the Lorentz force law, you have the force through this constant magnetic field. There's no electric field at first, okay? So the force on those free charge carriers will be QV cross B. If you do your right-hand rule, right, use your gun, okay, or laser in any direction. If you do your right-hand rule, then you can see that the free charge carriers are going to be pushed to either end of the bar. Your free electrons are going to get pushed to the bottom of the bar, and so that leaves a net positive charge at the top of the bar. So you have this charge separation. Once you have the charge separation beginning to build up, what happens is there's an electric field established within the bar due to the F is equal to QV cross B. The electric field will point from the positive to the negative charges. That establishes a field pointing downward through the bar. Now, as you can see from the free body diagram, which is here showing the forces on an electron in that bar, eventually what will happen is that you get so much charge built up on the ends of the bar that your electric field is strong enough to balance out the F is equal to QV cross B force from those free charge carriers moving through that magnetic field. At that point, the charge carriers in the center there, they come to equilibrium, okay? They feel an equal amount of force upwards as downwards. The downward force on that negative charge, of course, would be from the magnetic field, QB cross B. and the upward force would be from QE, all right? And they balance eventually. And then they just stay where they are and you maintain a certain voltage. Now, if you have a problem where the bar is sitting on some conducting rails, then the charge keeps moving, and the charge carriers will move through the circuit and power some external load, okay? So that's what happens. Now, this is exactly the external agency kind of thing that we were talking about on the previous slide, all right? This is the induced EMF. What's happening is that QV cross B Lorentz force, it's going to point down, and that would point opposite in direction, minus QE. So when Purcell and Morin said on the previous slide, right, you need a force, F external is equal to minus QE to balance the electrical force, hence the minus sign. Okay, well, our induced motional EMF there, that's the minus sign. And so they're related to each other via that minus sign, the EMF and the potential difference, okay? The EMF is the one doing the work, and the charges are the ones receiving the work, right? And they're related by a minus sign. So the EMF is the external agent. It's the cause, and the potential difference is the effect. And like so many cause and effect relationships in physics, they're related by a minus sign. So you could write your potential difference between the exact same 2 points, say on either side of your battery or whatever, or on either side of your bar moving through your electric field, and you'd have delta V is equal to the negative integral of E dot ds, which would equal to the negative EMF. Or you could write your EMF as the integral of E dot ds, okay, for our motional EMF problem. Okay. So now we have our definition of the EMF. The EMF is equal to the integral of E dot ds. But via Faraday's law, okay, our integral form, which we covered in a previous lecture, it's also equal to negative d phi b dt, where phi b is your magnetic flux. Remember, we defined our magnetic flux as the integral of b dot da. Okay, it's how many magnetic field lines are piercing through some surface A. Okay? Okay. So we have the EMF is the integral of E dot ds is equal to the minus d dt of the integral of B dot dA. Now, we need to take our little time machine back to calculus 3, okay? Remember Stokes' theorem? Stokes' theorem is for vector fields, and what Stokes' theorem says is that if you do a line integral for some vector field, E dot ds in this case, right? Then that's going to equal to the integral of the curl of that vector field, del cross E dot dA, okay? So the line integral of your vector field over a loop is going to equal to the curl of it integrated over your surface. That's Stokes' theorem. Therefore, what we can do is write our integral of E dot ds using Stokes' theorem as the integral of curl of E dot dA. So the curl of E dot dA, now going back to our top equation, which included the integral form of Faraday's law, right? We can say that the curl of E dot dA, the integral of that, is equal to negative d dt of B dot dA. Since these two integrals are integrating over the same surface with area A, right, then we can set their arguments equal to one another. And then we have the differential form of Faraday's law. The curl of E is equal to negative dB dt, okay? Now, we know that the magnetic field may be a function of both position and time, and not just time. So what we usually do is we write our expression this way. The curl of E is equal to the negative partial with respect to time of B, okay? All right, now let's discuss this in terms of Faraday's original experiment. It's worth noting that Faraday probably didn't know most of this math, okay, but he was a really great experimentalist. So what he was doing is he was using those currents that he was picking up in the coils as detectors of the electric field. So here we go. His original experiment involved primary and secondary circuits or coils. The primary coil was attached to a battery and a switch. And then the secondary coil wrapped around the same center there. This is a sketch from his original lab notebooks. So the primary coil surrounded the secondary coil. The secondary coil was not attached to a battery. It was just an independent little coil all on its own. Okay? So what Faraday noticed is that when he closed the switch to the battery, that he observed a spike in the current in the secondary coil. And then that spike went away, and there was no current flowing in the secondary coil. And then he saw another spike, but in the opposite direction when he opened the switch back up, when he was done with the experiment. All right? So what he was doing is he was detecting what he had in the primary coil. When he closed it, he created a current. Basically, this is a solenoid, which creates a nice uniform magnetic field inside that solenoid, okay? When he closed the switch, that magnetic field changed in time, going from 0 to some constant value given by mu naught Ni, okay, which is the equation for the magnetic field in the middle of the solenoid. So it varied in time for a brief amount of time. When it varied in time, that magnetic field, it induced an electric field, okay? It induced an electric field. That electric field created a current in the secondary coil, which he detected, okay? So he was using his currents as little electric field detectors, basically, all right? Let's do an example problem from Knight's textbook, Knight's second edition of his textbook in chapter 34 that I think will help cement it. Now, I'm not just doing that straight up example. I'm going to add on to it, make it a little more challenging for all you. Okay, so here we go. A 4-centimeter diameter solenoid is wound with 2,000 turns per meter. The current through the solenoid oscillates at 60 hertz, and it has an amplitude of 2 amps. So what is the max strength of the induced electric field inside the solenoid? All right, so first let's discuss the conceptual bits here. All right, we have a solenoid, okay? Inside of the solenoid, that's going to generate a magnetic field. We learned about that before. Now, since the current in the solenoid is changing with time, and the magnetic field is directly proportional to the current, then that means that the magnetic field is also changing in time. When the magnetic field changes in time, that's going to induce an electric field, okay? And then that's what we're going to report on here, the max strength of that induced electric field. Now that we've discussed the concepts, let's go ahead and put some math to it. So, remembering our solenoid, if you've forgotten all about it, a solenoid is basically a coil of wire, okay? The wire is coiled in a helical fashion around some constant radius. Usually you have some sort of core and you wrap it around it, for example, okay? And then the equation for the magnetic field inside that solenoid is B is equal to mu naught Ni, okay? Mu naught is the permeability of free space. The magnetic field in the interior of the solenoid can change if you put something with a high magnetic susceptibility in there. But for now, we're just assuming that the solenoid is empty inside, okay? So here you have mu naught, which is 4 pi times 10 to the minus 7 in SI units. N is the number of turns per unit length, okay? So that's how tightly you wrap it. And I is your current, okay? So that's your magnetic field strength equation. It's also important to remember, for the purposes of this problem, that the magnetic field inside a solenoid, if the solenoid is ideal, that is nice and straight and uniform all along the interior of the solenoid, and then it's basically 0 right outside it, okay? All right, so we are going to assume something that they didn't really tell us. We're going to assume that the current is oscillating in a sinusoidal fashion, and we're doing that, I'll be honest, just to make our derivatives pretty. And why not? He didn't tell us otherwise, so sure, right? So it's a sinusoidal function. So our current can be written as I is equal to I naught times sine of omega t plus phi. Now, here, I naught would be the max current going through the coils at any given instant, but it oscillates sinusoidally. So it oscillates at a certain frequency. That frequency is specified as 60 hertz, so that's 60 oscillations per second. But remember, the straight up frequency isn't what you plug into a sinusoidal function, because they all have periods of 2 pi. And so instead, what you plug in is the angular frequency, omega, and that's defined as 2 pi times f. So it's 2 pi times the measured frequency of 60 hertz, okay? Now, phi here is just a phase constant. And it's just set in there so that you don't have to start your clock right at t is equal, or you don't have to start your current going and time it perfectly with when you start your clock, okay? And it doesn't really matter for the purposes of this problem anyway. Okay, so we've got our current I, and that's going to be 2 amps, because that's I naught, times the sine of 2 pi times 60 hertz times t, plus our phase constant, which we can leave undetermined. Now, because of our equation for the solenoid, B is equal to mu naught N I, we can plug in and get the magnetic field for the solenoid, okay? B would be equal to mu naught, 4 pi times 10 to the minus 7 in SI units, times 2,000 turns per meter, which I've just written here as meters to the negative 1 power, or inverse meters, times 2 amps, times sine of 2 pi times 60 hertz times t plus 5. Okay, so that's our magnetic field. So you can see that our magnetic field is oscillating and changing in time. Now, we're going to apply the integral form of Faraday's law here to solve first, all right? Now, what we're doing is we're trying to find the maximum electric field strength within that solenoid, and they don't really specify where right now, okay? They don't specify where, so we're going to get to that in a second. So what I'm going to do at first is I've drawn a little top-down view of our perfect solenoid here. So this is a top-down view. Remember, there's cylinders from the top down, and so when you look down at them, they should look like circles. So this is our top-down view. Now, the radius of our solenoid is going to be 2 centimeters because it's specified the diameter is 4 centimeters. And so what we're looking at is we're looking at some point, at some position off the central axis, at some distance that we're going to leave undetermined, but we'll call it R, okay? And we're going to look at what the electric field strength equation would be for that point R. Now, once we pick a point, we're not going to change it. R isn't changing. And so that means that if you look at the integral form of Faraday's law here, we have our minus d dt of B dot dA. Okay, that's going to be our induced EMF. Okay, so if you're looking at the interior of a solenoid, then sure, this one changes with time, but it doesn't change spatially, right? The magnetic field at some instant in time, for example, if you take a little snapshot, will be the same all throughout the solenoid's interior. It doesn't depend upon R. So when I do that integral of B dot dA, basically I can pull that outside of my integral because there's nothing in there that when I integrate over dA is going to change, okay? Now, here's another point. If I pick a fixed point inside the solenoid and don't change it, then the dA shouldn't change with time, okay? All right. Also, if I pick a fixed point inside and don't change it, then I know what the integral of dA is going to be. It's just going to be pi r squared, which is the area of a circle. Not very interesting, but easy to do. Okay, so that means that my negative ddt of the integral of B dot dA I could write as just my area, pi r squared, times minus dB dt. All right? Way to go me. Okay, so that's my whole right-hand side. Now, at this point here, R, what I'm going to do is I'm going to integrate E dot ds as I walk around that circle. Okay? I'll show you why in a second, but that's definitely what I'm doing. I'm going to walk around that circle all the way from start to finish. So if I do that, then my ds becomes RB theta, and then I integrate theta from 0 to 2 pi. Now on this slide, I didn't want to type all that out, so I just skipped to the end, and I wrote 2 pi RE for my value of the integral of E dot ds. Yet again, I'll show you why in a second. All right, so this is my setup. Now, I can simplify that expression from the previous slide, and I can write my electric field as negative R over 2 times dB dt. Plugging in and finding for what dB dt is, remember that if you take the derivative of a sine function, you get a cosine function. And if you take the derivative of sine omega t plus phi, you're going to get omega times cosine omega t plus phi. So then I multiply that times all those other constants that appear in there, and I end up with an electric field strength of negative R over 2 times mu naught n omega I naught cosine omega t plus phi. There you go. Now the question asks for the max electric field strength inside the solenoid, all right? So there's a few things that we have to think about if we want the max electric field strength. So first of all, we want our cosine function to be maximized to give us the most electric field that we can get. Now that would happen here when cosine of omega t plus phi is equal to minus 1, and then that would give us the most positive value, the largest positive value for our electric field. Okay, so that maximizes our electric field strength. The other thing that needs to happen is that you see here that our electric field is proportional to R. So since we know that the magnetic field inside there is uniform all throughout, then I can just pick the value of R that would give me the max magnetic field, or the max electric field. And that would be right at the edge where my wires are. So still inside the solenoid, but just barely. And then we would set R is equal to 2 centimeters. So plugging all those numbers in, I have mu naught over 2 times 0.02 meters times 2,000 inverse meters times 2 pi times 60 hertz times 2 amps. Phew, that was a lot. And that gives me a maximum electric field strength of 0.019 volts per meter inside my solenoid. Now, if we want to just say at any given instant in time, what would that be? Well, you can see that your electric field strength would vary in time, wouldn't it? This isn't the max. It's going to oscillate. I mean, the problem asks for the max, but the electric field strength is going to oscillate. I think that's a key important point here. And so how would it oscillate? Well, at R is equal to 2 centimeters, which is the point we picked, it would be negative 0.019 volts per meter times cosine of 2 pi 60 hertz t plus 5. Okay? So your electric field is going to be changing in time just like the magnetic field. But we're not done. That's what Knight asked for. We're going to go just a step further. All right, what does this look like and what are the implications, and can we use the differential form and verify that the differential form of Faraday's law works here? Okay, so first of all, let's get the concepts down and then we'll go on to the differential form. So here's a little sketch from Knight's textbook, and it shows our solenoid, and let's just pretend for just a second that we're examining a slice in time where the magnetic field strength inside the solenoid is pointing upwards, and that would be if you are looking down on the solenoid, the current would be flowing counterclockwise according to you as you look down. That would cause the magnetic field pointing upwards here, okay? And let's look at a snapshot in time where that magnetic field is increasing in time, in strength, okay? So we have the magnetic field pointing upwards and increasing in strength. Now, picture in your head the thing that we had said before about which way current would flow in a loop, okay? So let's pretend for just a second that inside of our solenoid, we've placed a secondary coil, just like Faraday did, okay? We have a little secondary coil, maybe it's just one turn even, inside there, okay? Now, at this point, our magnetic field is increasing in strength upwards. And so according to Lenz's law, what does it want to do? Well, what it would do is it would induce a current in the secondary coil that would oppose that change. In other words, if the magnetic field is pointing up and increasing in strength, it would generate a magnetic field that points down to compensate for that. Now, if we have a little circular loop, a secondary coil inside of our solenoid, we could say magnetic field would point down or downward from our secondary loop, and that means that our fingers would curl clockwise, right? The induced current would be clockwise. Now remember, current flow is in the direction defined as the motion of positive charge. So what would happen then is you would have an electric field that would be pushing it clockwise. Well, if it's a positive charge, that means that the electric field has to go clockwise too. So that is the picture that is shown here in the center sketch. What happens is you induce electric fields that make little loops. For this case that we've shown here, those electric fields are going to be clockwise looking down on the top of your solenoid, okay? So the induced electric field lines are make little circles in a clockwise motion here. And that's why I said I'd come back to it. We did our E dot ds because we want to follow the path of that electric field as it walks around. And so that's why we integrated E dot ds the way that we did in our circle, okay? I hope that's clear. All right, let's do the differential form. This problem has cylindrical coordinates. Solenoids are natural cylindrical coordinate systems, okay? Now, remember, when we were looking down on our electric field, here was our long axis. In cylindrical coordinates, we would call that our z-axis. The radial distance out from the z-axis we'll call r, and then the theta hat direction is the one that walks in little circles around the axis. So what that means is that our electric field has a theta hat component. But since it only walks in little circles around the axis and doesn't have any components up and down or radially, okay, then that means that the r hat and the z hat components are 0. So we can write our electric field as negative r over 2 mu naught mi omega I naught cosine omega t plus phi theta hat. Okay? Now, let's check that this obeys the differential form of Faraday's law. The differential form of Faraday's law is del cross E, the curl of E, is equal to minus partial V with respect to t. Okay? All right, we got to go back to our Calc 3 again. Okay? From Calc 3, if you have a vector field A and you want to take the curl of it, it's defined in this way. And I only love Microsoft's equation editor so much. I didn't want to type all that in. So I actually took a picture of it, and that's a picture of what the curl of a vector in cylindrical coordinates is from Calc 3. There it is for you, okay? Now, this one leaves it generic and it calls it A, okay? Ours is E. We're going to find the curl of our electric field. So now I'm taking the function that I've defined up here for E, and I'm taking the curl of it according to this equation right here. All right, we can see that we would have EZ, E theta, ER, EZ, E theta, ER. Well, since the ER and EZ terms are automatically zero, a lot of terms are zero trivially, okay? Now we can also see, if we look at our electric field equation, that it's not dependent upon theta, and it's not dependent upon Z explicitly. So since it doesn't have that explicit dependence, then those terms where it's taking the partial of, see here, partial of EZ with respect to theta, I'm sorry, not that one, the partial of E theta with respect to Z, okay? There is no Z component. So that would be 0 too, trivially, all right? The only non-zero term for our specific case here ends up being the 1 over r partial with respect to r of r times E theta, which is this term right here in the z hat direction, the first term in the z hat direction right there. So this would be the curl of E is equal to 1 over r partial with respect to r of r times r times E theta, which is negative r squared over 2 times mu naught n omega I naught cosine of omega t plus phi. Okay? Now when you take that partial, when you take the partial with respect to r of r squared, you get 2r. And then the 2 up top cancels out with the 2 down bottom, and you end up with 1 over r times minus r mu naught n omega I naught cosine omega t plus phi. And this is all in the z hat direction because of the definition of this curl of E. Then the 1 over r cancels out with the r, and you end up with negative mu naught n omega I naught cosine omega t plus phi in the z hat direction. So that's our curl, okay? That's our curl. Now, here it is up top, copied and pasted again. Our differential form of Faraday's law is the curl of E is equal to minus dB dt, okay? So, our curl of E ended up being negative mu naught n omega I naught cosine omega t plus phi in the z hat direction. And a few slides ago, we said what dB dt was. So if you don't remember, minus dB dt would be negative mu naught n omega I naught cosine omega t plus phi. Now we know that our magnetic field points parallel to the z-axis. So, of course, that's going to be in the z hat direction. So, proof, done. Differential form of Faraday's law works. Happy day for us, okay? Now, one thing that I want to point out is that when you do the integral form of Faraday's law, you have to go through some mental gymnastics to figure out which way that induced current or the electric field would go. We went through those mental gymnastics a couple of slides ago when we talked about, it wants to oppose the change and all that kind of stuff, okay? So, if you do the differential form, if you're able to do the differential form, you don't have to go through those mental gymnastics because it falls right out, okay? It fell right out. The direction fell right out. So that proves, in a way, proves for us, for this situation, Lenz's law is working. Yay. Okay, so let's sum up and kind of come to the end here. The electromotive force is the cause. The electric potential is the effect. So they're different via a minus sign. Our EMF is defined as the integral of E dot ds, and our potential difference is negative integral of E dot ds. But I'd like to say one more thing about this. They're different in other ways too, okay? Sorry, you don't get off that easy. Way back when we first introduced this equation for the electric potential, we were talking about the electric potential for static charge distributions, right? We would set up some system of static charges. We would calculate an electric field or an electric potential based on that system of static charges. Well, things are a little different now. If you have electric fields and hence potentials created by only static charge distributions, then the curl of the electric field is always zero. And that's because there's no magnetic field unless those charges start to move, right? You only get magnetic fields from moving charges, okay? You don't get them from stationary ones. And so if you don't have a magnetic field, then you definitely don't have a changing magnetic field in time, which would make the right-hand side of our differential form of Faraday's law, by definition, zero. And so you would end up with the curl of E is equal to zero for these situations. Now, if the curl of E is zero, they definitely can't make little loops. Remember what a curl is, right? A curl is something curling around, making little loops and little circles. If something doesn't do that, right, by definition, the curl of E is zero, they can't form loops like the ones shown here in our previous problem, where the electric field circles back around on itself. That's not going to happen with a static charge distribution. It's just not. When electric fields are created by static charge distributions with no curl, they do no work in closed loops. We said this explicitly in a previous lecture. And here's the picture to prove it, okay? Here's the picture for an electric field indicated here in blue, pointing to the right, and we have our little star charge here, walking a closed loop. Now you can see that it would go, when it goes perpendicular to the electric field, those components are zero by definition of the dot product. When it goes with the field, you get a positive value for E dot ds, and when it goes against the field, you get a negative value for E dot ds, and if it makes a perfect closed loop, they sum to zero, the positive and the negatives, right? So the work on a charge as it walks around a closed loop due to a static charge distribution is zero. They do no work in closed loops. That means that when the electric field is due to a static charge distribution, it's a conservative force, F equals QE, okay? But if you have an electric field that's been induced from a changing magnetic field, work can be done in a closed loop, okay? And it's non-conservative work. If you've got a circuit, this makes sense, right? Especially, I think, intuitively. Let's say that you've got a charge and it's moving its way around a circuit. Well, what happens when you have currents in circuits? The wires heat up. Why do they heat up? Because of dissipative forces from the resistance. Anytime you have dissipative forces, right, you've got a non-conservative force, okay? So that's one way to think about it, if that helps you remember. But basically what's happening here is the work is non-zero because the curl is non-zero. In other words, if that electric field can come back and circle in on itself, let's picture what would happen, for example, to a free charge that was floating around on the inside of our little solenoid. If you had some positive free charge floating around on the inside of our solenoid and you started this magnetic field up, what would it do? Well, it would induce an electric field that would make a little loop. So what would happen? Your positive charge would go whoop, right? And then you would reverse the direction and it would go whoop, and then it would go back and it would go forth, right? And it would sit there and it would make little circles, okay? So that's what your charge would do in the presence of that induced electric field. And it would do it all because the curl is non-zero. You can see that it's non-conservative, right? Because what's happening here is work is done on that charge, okay? And it's done over that closed path. Okay. All right. I hope that's clear. And if it's not, let me know, and I'll see you in class.